welcome back to the lecture series. I thought maybe I start by giving you a kind of review of where we have come during the course of this lecture series. So this was the mountain where we, so to speak, learned how to implement a neural network and how to do backpropagation in order to train it. And since then we've looked at a series of applications. So the first was just to show that we can represent basically arbitrary functions, including an arbitrary image in terms of a neural network. Then we said we can use neural networks for classification. So you give me an input like an image. I tell you what it means if I have seen many training examples. Then we said that for the particular purpose of images, it's actually good to exploit translational invariance, and you can build a neural network that uses many fewer weights in its construction. These are the so-called convolutional neural networks. Then we went to something that is no longer supervised learning, but which just tries to encode as well as possible given input examples. So these are the autoencoders. Then we had a brief remark about how to do unsupervised learning in the sense of trying to visualize high-dimensional data in a meaningful way that would give you, for example, clusters that you can recognize of data points that are similar. And so that was dimensional reduction, the TSNE method. And then we went to look at more sophisticated networks. And the first one was recurrent networks, that is networks with memory. So that is when neurons also depend on what has come before in terms of the input and in terms of their internal memory state. Then we briefly mentioned word vectors. So that's just useful for a particular application of recurrent neural networks when you want to analyze a full text, which can be seen as a string of words. But how do you represent these words? You can just label them in a big dictionary. That would be the very basic version. But you can also invent these so-called word vectors where different components of the vector have different semantic meanings. And then you can even do calculations with such word vectors. And then very recently now, we started by looking into the big subject of reinforcement learning. So reinforcement learning is really much bigger than I can explain it here. This is basically the kind of learning that will possibly take us to real artificial intelligence, because it's learning where you don't need to specify in detail all the correct answers to all the correct training examples. You just give a general hint as to what you consider useful or good, and then the neural network will try to develop strategies on its own. And so to make this distinction clear again, I already mentioned it last time, but here it is again in terms of pictures. In supervised learning, you always would have a smart teacher training the student, and the student imitates the teacher. But then, of course, the final level is more or less limited by the teacher. And reinforcement learning is very different. In reinforcement learning, it's like you imagine a very smart student or even a scientist who just tries various things and then keeps the things that work and tries to build on them and improve even further. And then hopefully the final level is unlimited. Okay, so this is something I already said last time. The general setting is you have an agent interacting with an environment. The agent undertakes some actions like moving around or grabbing something that change the environment, and the agent also observes the environment so that it can tailor its actions to the observations. And that is the basic premise of reinforcement learning. So to illustrate it here again, this is my agent, this is the environment. What really happens inside this black box that is the reinforcement learning agent is the following. So you take an observation and you convert, and this observation indicates that the environment is in a certain state. Maybe you have partial information about the state, maybe you have full information about the state, so these are then details that you can distinguish. But at least you have observed some state of the environment, and you want to map this into an action, into the action that you will perform next. And this mapping between state that you observe and the action that you want to do, that is called a policy. So a policy is simply something like a strategy. And a good agent would have a good policy that is good for some purpose, and we have to discuss how you measure this. And here again is a way to represent the situation. Here we have our little robot. Let's say it can move around, and here are some boxes, and now I have to tell you what is the goal of this game. If I don't tell you, or if I don't tell the robot, then it can also not become better at the game. And so maybe the game consists in trying to pick up these boxes as quickly as possible. So the state could be the position of the robot. The state, however, could also be the full image of the full surroundings. So even there are different choices. And then the actions, in this case, would presumably be the moves into the different directions. But as I said, we also have to specify the goal. So in addition to specifying states and actions, we have to specify what is considered good. And this we do by specifying a reward. So for example, we would say, whenever you pick up a box, you get a reward of +1. And whenever you don't do anything useful, there's just a reward of 0. Or maybe there's even a negative reward during time steps where nothing good happens, because you want to punish the robot if it takes longer to actually pick up all the 3 boxes. So these are again the details, but they will be important because they will determine which are the optimal strategies. And so I already told you that the strategy is somehow encoded in this policy that maps state to action. But the question is, how do you want to do this in detail? And there are problems if you have immediately a deterministic mapping from state to action. Because then, I tried to make this clear last time, if in the end you want to say, okay, let's see, how do I increase my reward? You would have to say, well, what would have happened to the reward if I had taken a different action? And that's a fair question. But then the problem is that a different action not only means that your robot does something different, but it also means that then the environment reacts in a different way. For example, if it first goes to one particular box and picks it up, then of course the environment has changed because this box is no longer there. So the actions have consequences for the environment, and unfortunately in many cases you cannot predict what would happen to the environment if you do certain actions. Yes, you don't necessarily have a model for the environment. And so that brings us to this big field of model-free reinforcement learning. And the one that I want to discuss first works with probabilistic action choices. So you have your policy, but it's no longer saying, oh, okay, when you observe this state, you have to do exactly this action. It just gives you probabilities for different actions. And then you can play around with these probabilities. So by updating these probabilities, by changing them slightly, you can change your policy. And then you can see what happens to your rewards. And if you have changed them in the right manner, then at least on average, over many attempts, the reward should increase. Okay. And so now the situation is displayed here. The policy in this version of reinforcement learning, the policy is really a probability distribution. So it takes the state at time t, I call it st. It takes the state and says, what are the probabilities for different actions? So what's the probability for some action at given the state st? And for example, the best thing to imagine is you have only a small set of different actions, like these 4 movements into west, east, north, and south. And then at would just be represented by these 4 possible choices. So you could take it to be one of 4 numbers, 1, 2, 3, 4. So then specifying this policy would mean specifying these 4 probabilities for moving into the different directions given a certain state. And now again, it depends on how you represent the state. The state could be, for example, these x and y coordinates of the robot. Then for every possible x, y coordinate, for every possible position, there would be a different probability distribution for the different actions. So you can see already that specifying the policy may involve a lot of data. And while it may still be possible in such a simple case to make it in terms of a table, so that would just mean every position has a different table of 4 probabilities, eventually you will run out of memory, so to speak, to specify your probabilities for the policy. And eventually you will have to try to calculate the policy via a neural network, and we will come to that. But at the moment, this is the general abstract definition. A policy is a probability distribution giving the probability of taking a certain action given a state S. And now you see there's this parameter theta that I introduced. That's because we want to be able to change our policy. And the case that we will consider most will be if you have a neural network, and then the theta, as usual, represents all the weights and biases in this neural network. So theta can in reality mean 1,000 different numbers, namely the weights and biases of the neural network. Okay, so that at least explains the setting of probabilistic policy. I hope the setting is clear. Yep. Okay, so now, as I said, there are various ways to represent the policy. You could make a little table if this number of states and actions is not so large. But in general, you will want to use a neural network, yeah? Because maybe even the state that you observe is a full image already, and maybe the actions, maybe there are also relatively many of those, and then it's completely impossible to do it via a table, but you can always use a neural network as a general function approximator to approximate your policy function. Okay, so just to make it clear once more, here if the player or the little robot is represented by this red dot and the green dots are the places where you can pick up treasures, then these probabilities that define the policy could look like this. If I'm at this particular position, then probably in a good policy, the probability to move up should be highest, because that's where I can pick up the treasure. And I guess I already implemented this. So the value of pi is the probability, is 0.6 in this case. So the policy has the highest probability to move up for this particular state. If I place my robot at a different position, maybe above one of these green circles, above one of the treasures, then the probability to go down should be largest in an optimal policy. You also see that I can implement also a deterministic policy. That would be the limiting case where only one of these probabilities is 1 and the others are 0. Okay. Now, suppose you implement this action, you really go up. Then, of course, things start to change. At least, certainly, the state changes in that you have changed your position. That's the simplest change. Also, maybe the state that you observe changes, or the overall state of the environment changes in the sense that if you pick up one of these boxes, then it vanishes from the board. And then there could be other things that happen even without you doing anything. There could be other players, like, for example, moving around probabilistically or something like this. Yeah? So many things can happen in the environment. And so the way we like to model this is to say that also the environment on its own is a stochastic process. So given a certain state of the environment, you can describe what's the probability for the environment to go into a different state. And maybe it does not only depend on the current state, but also on the action you took. Yeah? But given the current state and the action you take, you should be able to tell me what's the probability for the environment to go into a different state. And this would then be described by what we call a transition function. So this is a probability to end up in a state S prime, given that at the current time step we started out in a state S and we implemented the action A. Again, it could be deterministic. If it's deterministic, it just means that for a given state S and a given action A, there's precisely one state S prime that you will end up in. So this one will get probability 1, and all the others have probability 0. So that would be the limiting case for deterministic environment. Okay. So now we have these various probabilities. We have the probabilities that are involved in the policy, that is our strategy, to take different actions. And we have these probabilities for the environment to make these transitions between different states. And so now we think of the whole thing like a movie or a trajectory. Yeah? So at every time step, the policy decides what action is to be taken, and then whatever has to happen because of this action happens, plus there may be other changes in the environment, and we go to a new state, and then the same thing happens again step by step. And so this whole trajectory or movie, I want to abbreviate here. I want to call it tau, tau for trajectory. And so this consists of the sequence of all actions that I take and the sequence of all states that I take. Maybe I always start out from the same state in the beginning, but after that it depends on the details of how these probabilities look like and what is actually realized. So why I want to calculate the probability for a whole trajectory is simply because in the end I want to do average things. I want to average over many different trajectories. I, for example, want to calculate what's the sum of all rewards on average when I go through many trajectories, always with the same policy, because that will tell me how good is my policy. Yeah. And so this is written down here. So P of tau is supposed to be the probability to observe one particular trajectory, so the probability to observe one particular movie, so to speak. And it's not difficult to calculate. I just have to multiply all the probabilities of the various steps. So maybe the state that I start in is already fixed. Then the next step to take is to evaluate the policy and to ask, okay, what's the probability to take a certain action? And then given this action and also given the current state, what's the probability that my environment makes a transition to a new state as t+1? And now this would be the product of these two probabilities only for a single time step, but of course to get the probability for a given trajectory, which has many such time steps, I have to multiply all these probabilities. So policy, transition, policy, transition, policy, transition, one after the other. Yeah? And that's then the probability of this particular trajectory defined by these particular sequences of actions and states. And if I took different actions and states, then I will arrive at a different probability. Yeah? So now, at least conceptually, that's a nice concept. Of course, to calculate it would still be very hard. But now I can ask something very important. I can say, well, let me look at the rewards. Maybe I sum them up over the full time interval. And let me see what's the average of the sum of all the rewards, because that's what I'm really interested in. And so, just a little bit of notation. The overall reward, or the sum of all rewards that I get at the various time steps, is often called return. So that's the overall return, what I get out of this one game. And I am not so much interested in what is the value of this return for a particular realization, for a particular trajectory, because I know things are probabilistic, so I want to calculate the average. I want to calculate the expected return averaged over all trajectories. And so what do I have to do seems to be very simple. So the return I will call capital R. Capital R with a bar means the average, or sometimes I also write the E for expectation value of R. And then what is that? Well, as for every average, I just have to sum over all possibilities the value of whatever I want to average times the probability. So the value is R of tau. That is the return for this particular trajectory. And I multiply it by P of tau. That's the probability for this particular trajectory. And then I have to sum over all the trajectories. Now the sum over all trajectories is of course a gigantic sum, yeah, because each trajectory is specified by all these different actions and all these different states. So this sum is actually a repeated sum over all possible A0, A1, A2, S1, S2, and so on. So it's a very high dimensional thing, a repeated sum over many different variables. But that's okay. Yeah? And of course, you have encountered similar things in if you do quantum mechanics and express it by this Feynman sum over paths, then you also have to sum over all possible trajectories, and you would do it similarly. Okay. So one extra thing I want to mention: why do I assign this theta to my probability of a trajectory? Well, the reason is that the policy is parameter dependent. The policy depends on this parameter theta, which again for a network would be all the weights and biases. So that also means the trajectories that I observe, the probability for that depends on these parameters. That's a good thing, because that means I can change the average return by changing these parameters in here. Otherwise, I wouldn't have a chance to optimize my return. Okay, so now what I want to do is really just optimize this average return by changing these parameters theta. And we don't have so many ideas in this game. We just try to do a gradient ascent. Yeah? So we know we have some quantity, we call it R, the return, that depends on parameters theta. Let me change these parameters along the gradient of this quantity with respect to the parameters. So in the end, I will say the change of theta will be along dr over d theta. That's the gradient of R. Now again, theta really stands for a long vector of many, many different parameters. So this gradient is really a vector because there are many thetas. You could call them theta j and have an index there. Okay, but that's it. So that's why this whole idea is called policy gradient. You take the gradient with respect to the policy parameters. So now I have to stop and ask, is this slide clear? Because that defines the concept and has the important definitions. It seems clear for now. Okay, good. So now let's try to do this gradient. We have a little bit of experience in taking gradients. Let's try to see what happens and whether we can simplify the resulting lengthy expression. Okay. So now I just go ahead and straightforwardly calculate the gradient. Again, I remind you, the theta here, really there would be many entries in this theta vector, and I could calculate the derivative with respect to theta 1 or theta 2 and so on. But of course, I don't need to display this explicitly here because there are enough indices floating around. Okay. Okay, so dr over d theta. Well, so now I literally just took the expression that I had on the previous slide. Maybe I should remind you. So there's a sum over all trajectories. For each trajectory, there's this product over all times of these probabilities. And then there's also the return for this particular trajectory. So now here you recognize the sum over trajectories, the return for this particular trajectory. Okay, and then I have already gone one step further. So here in principle there would be the product of these subsequent probabilities. So always policy, transition, and so on. But now if you take the gradient with respect to such a product, like here, if you take the gradient with respect to this, then there are many terms in this product, namely all the policy probabilities, that depend on theta, and that theta is what you want to take the gradient with respect to. Yeah? So how do we take the gradient of a product? Well, we have to take the gradient with respect to the first factor, and then with respect to the second factor, and with respect to the third factor, and we have to sum all of these contributions. So that's how a new sum will arise. So for each time step t in this product, I will get a gradient with respect to theta of the policy in this time step. And in the end, therefore, I have to sum over all these possibilities, because it's a gradient of a product, so it becomes a big sum. And that's what happens here. So this is the sum because I took the gradient of a product. And in order not to confuse the notation, now this product I take over something that I call T prime. Otherwise there would be confusion. So T, any given T is the time at which I want to take the gradient of this policy. Now you should protest and say, well, in this product you still take the old product over all times, and there's the policy probability for all the times. Shouldn't we have taken the derivative of one of those, namely at time t? And the answer is yes, of course, you should have taken the derivative of one of those. So this would be wrong if I didn't compensate for it. So what I do here is a little trick. I say, here's the gradient that I really should take. That is the gradient of the policy at time t. And that should eliminate the policy at time t from this product. But since this is still included in this product, I have to make this good and divide by this particular policy probability at time t. So is this clear? It's the gradient of a product. So again, I have to take the gradient of the various factors and add all these different possibilities, and that's what I did here. And of course, there's a reason why I wanted to write this product already in the same form as before, because I then can take it all again and write it as the probability of this particular trajectory. Is there a question already? Some confusion maybe? Maybe you just go ahead and tell me what's the confusion. Oh, not yet. Okay, good. So, and then there's a little final trick. If you have the gradient of something, the derivative of something times 1 over that something, you can also always write this as the gradient of the logarithm. Yeah? Because that's just simply what results from the gradient of the logarithm. This also is useful in statistical physics. You could say this is why the logarithm of the partition function is such an important concept. Okay. So now I can say this product here over T prime again is nothing but the probability of this particular trajectory tau that is defined by the sequence of A and S. So this is just P of tau. So there's P of tau, there's R of tau, there's this logarithmic derivative, and I sum over all trajectories and sum over all times. Now if I collect everything, I can say that since here I have still the probability P of tau for this particular trajectory to happen, and I sum over all tau, that's nothing again but an average over all trajectories. So that's my expectation value over all trajectories in the same sense that I wrote it down here. Here I had the expectation value of R, so it was the sum over tau, P of tau times R of tau. Here now I have something slightly more complicated because I multiply the R of tau by this logarithmic derivative. So when I write it now as an expectation value over all trajectories, this expectation value no longer just includes the R, but also this logarithmic derivative. And, not to forget, we had the sum over all t, which came from taking the derivative of a product, and this also occurs here, sum over all t. So this is the t that occurs in this logarithmic derivative. Yeah? And so now we have collected everything. The gradient, which is important for our update of the parameters theta, looks like this. dr over d theta is the sum over all time steps, expectation value of the return of the full trajectory times this logarithmic derivative of the policy probability at this time step t. Now it may still at first sight seem a little bit unfamiliar certainly, and maybe a little bit complicated, but I should remind you that given our challenge, this is actually very simple, because our challenge is we have this policy, it gives us some return. That return is stochastic because also the policy is stochastic and the environment is stochastic. We want to get the best strategy. And all we have to do is now the following. Run a lot of trajectories. For each of the trajectories, calculate this return R, which is simply calculated according to the rules of the game, whatever they are. So it's just a number. And then look at which actions and states you went through for this particular trajectory. Calculate again the probability for taking this action given this state for each of the time steps, and calculate its logarithmic derivative and sum this over all times. And then finally do an average over all trajectories. So for each trajectory, my task will be to calculate this product of R, the return, with the sum over t of the logarithmic derivative of the policy. And then I just average. Yeah? And that will teach me how I should update my parameters. And of course, in principle, I should average over all possible trajectories, but there are maybe infinitely many. And so what I will do is what we have already learned before. I will do this stochastic sampling. So I do maybe 10 or 100 trajectories. I average over those, and I say this is a good enough approximation for this expectation value. Yes, there was a question, I believe. Yeah, in principle, we can have problems here. That now depends really very much on how this is, how the parameter dependence looks like. So the typical thing would be, say, imagine just a neural network, yeah? And imagine a sigmoid function, just as a simple case for an output that lies between 0 and 1 and could be interpreted as a probability. Then it will never become precisely 0, and that will save me, so to speak. Yeah? But it's true that so if your thing, if this doesn't converge as fast as you like it to converge, it's a good idea to look at how these probabilities really depend on the parameters. Yeah? And so also in neural networks, it can depend very much now on the how you parameterize or which nonlinear functions you choose for the last layer of your neural network, for example. Yeah? So this is all true, but in practice, this will not be the problem. Okay, good. So as I just said, we will use this formula and interpret in the sense of stochastic gradient descent. So instead of really taking an expectation value over all possible trajectories, we just sample a few. And then we already take a step with respect to our parameters in the usual way. So we have a learning rate eta, and we take a step in the direction of the gradient. Okay, so this is at first sight maybe a lengthy story, but given the challenge that we face, it is really quite remarkable that this works. And I want to point out again a very, very remarkable step in all of this, namely the environment dynamics only enters into these transition probabilities. But when I take the gradient, I only affect the policy. Only the policy depends on the theta. The gradient need never be taken with respect to the dynamics of the environment, and actually I never need to know these transition probabilities. They only made their appearance, so to speak, as an intermediate step so that I could write down these formulas. And then finally, when I collected everything, I only need to know the gradient of the policy and nothing else. So you can apply this actually to the real world, yeah? A robot running around in the real world. It would be super hard to even just get an approximation for these transition probabilities that model the dynamics of the environment, but you don't need to. You just need to apply this formula. So I should also say, of course, there's still one, there is one assumption in trying to write down the transitions, the probabilistic transitions of the environment in this way. And the assumption here is that the environment is Markovian in this description. Markovian means that if I know the state and I know the action that I take, then I know enough, then I know everything that I need to calculate the probabilities for the next state. I don't need to remember the state 3 time steps ago. These probabilities do not depend on the state 3 time steps ago. Now you might say, well, that is a severe restriction because maybe many things do depend on the memory, on what happened in the past. But then there's an old trick to still fit it into the same framework, because you can say, well, maybe there are additional unobserved state variables that produce this kind of memory effect. So in physical terms, it would be, for example, if you want to formulate the trajectory of a particle only in terms of the position, then maybe knowing the current position is really not enough to know the next position, yeah? Because really for the dynamics of a physical particle, you would also need to know the velocity and not only the position. Yeah? But if someone only gives you the position and you don't know the velocity, then you would say, oh, this seems to be a system with memory. I also need to know what was the position not only at the present time step, but also the position 1 microsecond ago, because of course using these two positions you could guess what is the velocity. Yeah? So in this sense, if you look only at the position, it seems like as if you are faced with a non-Markovian dynamical system, where you need to know the position not only at this point in time, but also at the previous point in time. On the other hand, if someone smart comes up and say, no, let's not just look at the position, but also at the velocity of the particle, then for the usual dynamics in classical mechanics, this is enough to calculate the next position and also the next velocity, if you know the forces and so on. Yeah? So by extending the number of variables, it is often possible to go from a non-Markovian to a Markovian description. Or you can also reverse this story. You can say, I start with a system that has many degrees of freedom, many variables that I need to fully describe the state. Let me look at the trajectory, but let me forget half of the variables. Then it will seem to you that even if the original dynamics was completely Markovian, it will seem to you as if the dynamics is non-Markovian, simply because you eliminated so many variables. And there's an additional aspect to this story. If you start eliminating variables that you don't observe any longer, it also may mean that the dynamics seems to become stochastic. This is because even if in principle it was deterministic, you don't know the values of these other variables. So it seems to you that even if you reproduce the same values of the observed parameters, one time it reacts in this fashion, the other time it reacts in another fashion. But this is, of course, simply because you didn't look at all the other variables. Yeah? If I have a molecule inside a gas, and I don't keep track of the millions of coordinates and velocities of all the other gas molecules and only look at this particular molecule, then it seems to do a random walk and it seems to undergo a stochastic evolution. If I were to keep track in principle of all these million variables, then it would be completely deterministic Newtonian evolution. Yeah? So there are all these kinds of considerations which I'm a little bit sweeping under the rug here, but they are behind the story. But if you are not so familiar with this, you can for the moment just forget about this and trust me when I say, even though this seems at first sight a relatively restricted scenario, in reality it's a very wide-ranging scenario. Okay, fine. Good. And so again, the important thing is that our derivative only acts on the policy, not on the environment dynamics. We don't need an explicit model for the environment, so therefore this is called model-free, and this is very important for actual applications. We don't need to model the actual environment of the robot. Okay, and so now that we have derived this mathematically, it's good to step back for a moment and ask ourselves, what does it mean physically? Can we give it a qualitative interpretation? Because that's always very helpful. Yeah? Also so that you don't forget this formula. So let's have a very rough qualitative look at this. If I take the derivative of the probability or the logarithm of the probability, it doesn't matter. That means I'm trying to change parameters in the direction where this probability would get larger. It doesn't matter whether I look at the probability or the logarithm, because the logarithm is a monotonous function, monotonously growing function. So anyway, if I make the logarithm larger, I also make the probability larger. So the way I can interpret a step in this direction is to say It's a step into the direction of the parameters that will make my probability larger. Which probability? Well, the probability displayed here. This is the probability for taking action AT at time t given state st. So now you have to remind yourself, the trajectory, one particular trajectory was defined by the sequence of all states and actions. And now for this particular sequence, you ask yourself, how can I make the probability for one step inside the sequence, how can I make it larger? And actually, since you're summing over all times, you're really asking, how can I make, on average, all the probabilities larger? So in words, what you really do is the following. You take a trajectory, you calculate its return, okay, and you say, let me make all the probabilities of all the actions that I encountered, that I really took, let me make all of them more probable. That seems like a funny thing because you're doing it without regard, it seems, to the overall return. Yeah? You're just making all these probabilities larger. Now the good thing is you're doing it at a speed that depends on the return, because here you see the return enters. So if the return, for example, is 0, you don't get any contribution. If the return is really large and positive, you get a large contribution. You want to make these probabilities larger. If the return is large and negative, you even go in the opposite direction. You make your probabilities smaller. So you take all these probabilities of whatever actions you did in the sequence, and you make them either all larger or all smaller, depending on the value of the return. That still is a little bit funny if you think about it, because you can have trajectories where the return turned out to be really large. That means all the probabilities will get larger. But in such a typical trajectories, you have taken many actions, and not all of them were really smart choices. There will have been some which in principle were really stupid choices, but they were overcompensated by other actions. So the return turned out to be large nevertheless. Now this seems like a problem for this kind of approach, because it means you also improve the probability of bad actions. But as a matter of fact, this doesn't really result in a problem, and the reason is that these bad actions, if they are really bad, will more likely lead to a bad return than to a good return. Sometimes they ride along on all the good actions and still get a little boost in their probability, but much more likely they will occur during bad trajectories with a bad return. And so on average over all trajectories, their probabilities will be diminished. Now, what about the normalization? You see that maybe, so the question is, how did you define your rewards? Maybe you did define the reward sometimes positive, sometimes negative, but it's also perfectly permissible to always only define positive rewards. Huh? So maybe even doing nothing gives you a reward of 1, and doing something really great gives you a reward of 5 or 10. So then it seems like you always continuously improve all the probabilities, and that seems to counteract the normalization of probabilities, if you increase all of them. But the point is you can, well, the point is the way you express these probabilities through the parameters theta automatically should be set up such that you have a normalization of probabilities. For example, if we are talking about a neural network, and these probabilities will be in the output layer of the neural network, you would use something like a softmax function, which automatically includes the proper normalization. And so then you can trust me that in such a case, you can play around with the parameters arbitrarily. Of course, normalization will always be obeyed, and that will also be true here. Okay. Okay, fine. Now, for the following more detailed discussion, I want to abbreviate things a little bit. Let me just pick one of the parameters theta k that occur in our policy, and let me call the gradient of the whole of the probability of a given trajectory, let me call that capital GK. So this is still trajectory dependent. That's the first thing. I want to make it trajectory dependent so that later I will be able to do the averaging. Yeah? So now P of tau, if you remember, was the probability for this full trajectory tau. I take the logarithm of this. I take the derivative with respect to one particular parameter theta k. Okay, fine. Now you can work this out for yourself using the steps that we already did on the previous slide here. This derivative actually will only effectively involve the policy, because only the policy depends on the parameters. And taking the logarithm is a very smart move, not only because it also occurs here, but the logarithm of a product is, of course, as you know, the sum of the logarithms of the factors. And so that's why the sum over times appears here. So, okay, so this is sum over times, d log pi theta of this particular time step over d theta. And so then I can express all of what I wrote above as simply the expectation value of my return, my trajectory dependent return, with this trajectory dependent gradient. It's just another way to write it, but it's very useful for us. Okay, maybe I should stop at this point and again ask, are there questions here? So qualitatively, really, you just run many trajectories using your policy, which gives you the probabilities to do actions. You always take note of the string of actions that you actually took. You have to remember them, because at the end of the trajectory, you get a value that is the return. And then you multiply this return by this logarithmic derivative. To calculate this, you should know how your policy depends on the parameters, of course. And then you do this many, many times and average over all the trajectories. Okay, we will see later how this is really done in a neural network, but this is the task. And by this way, you will enhance the probabilities of the actions that were involved in this trajectory, and trajectories with larger returns get stronger enhancement. Okay. So now I want to discuss something slightly more technical but also interesting, and it will give us a little bit of experience in handling these different components of this formula. You see, the way I proposed to deal with this expectation over all trajectories was to say, let's just take 10 or 100, that's our sample, that's stochastic gradient descent, and then we take our step. So that's our estimate for dr over d theta, and then we take our step with respect to the parameters theta. The problem is that even though the expectation value, so I can take a batch, I can take the stochastic sample, and now if I average over many batches, of course I get the expectation value over all possible trajectories in my whole space of all trajectories, and so expectation value wise everything is fine and we're doing right. But the fluctuations of our estimate drawn from this small sample could still be very large, and indeed quite often they will be rather large. And so that's a challenge, and this is the challenge I want to explain now because there's a solution to this. So here you have the same formula again, but now I did something funny. I subtracted a constant called b from this return r. And so in short, using the notation that we had before, if I call this derivative capital G, then I now would be looking at the expectation value no longer of capital R times G, but capital R minus B times G. And so you ask yourself, well, is this something different? What have I done? But in fact, it's actually the same. So I can prove that to you by showing that the expectation value of some constant B times this gradient G is actually 0. And that's not so difficult to show because, of course, if the b is really a constant, I can pull it out of the expectation value. So really, I only need to look at the expectation value of this gradient g. Now remember how the g was defined as the d log p over d theta. P was really the probability for a given trajectory. If I want to average this over all trajectories, I should simply multiply this expression by p of tau and sum over tau. Yeah, that's what I do. Sum over tau, p of tau times the d log p. But now, if you look at this closely and use what d log p is, it's it's 1 over p times dp over d theta. And so the 1 over p cancels the p, and I just get d over d theta p. Now this is still not everything, but if I now sum over tau, the sum over tau of p of tau is simply 1, because my probabilities are normalized. The sum over all trajectories of the probability to get a certain trajectory is 1. So taking the derivative of this with respect to a parameter is simply 0. So that is a little calculation. If you didn't catch it right now, you sit down and do it again yourself, but it's really nothing more than what is written here. Okay, so this is the reason why I am allowed to add or subtract such a constant here without even changing my formula. So whatever this right-hand side gives will also be given by this right-hand side. It's the same. But the good thing now is, even though the expectation value is the same, the fluctuations may be different. So if you have two random variables and their expectation values are the same, obviously their variances can be different. And this I will exploit here, because now I can try to adapt my b such that the variance gets as small as possible. This is the trick. And so I should already now say the b is called a baseline. It's, so to speak, it's something like the average return, which makes it such that even if you started out defining your return to be always positive, by subtracting this, you sometimes get positive and sometimes get negative values. And that's better. Okay. So now, let me take this this combination that we encountered, return minus baseline times g. Let me define this as a new random variable. That's the random variable whose expectation we already know and we like, but whose variance we want to minimize. And I put index k just to keep track that I'm talking about the gradient with respect to a particular parameter theta k. Just to remind ourselves, there are many parameters theta k. Okay. Now let us just calculate the variance of xk. Well, the variance of any random variable is the expectation value of its square minus the expectation value squared, and we want this to be minimum. So this is a function of b. We want to minimize with respect to b. We want to find the best optimal baseline to make the fluctuations really small. Well, what I have to do is just I take the derivative of this expression with respect to b and I set it to 0 if I want to find the minimum with respect to b. So at least that will give me an extremum, but I promise it's the minimum. Okay, and if you do this little calculation, you actually find a formula for b, and it's just this. It's the expectation value of g squared times r divided by the expectation value of g squared. So you see it's almost something like the average return, which would make sense, right? If you had to guess here what is the good baseline to subtract, you would say, oh, let me just subtract the average return, because then sometimes I will be positive, this difference will be positive, sometimes negative. That seems to be a good compromise. It turns out it's slightly more complicated. I still do an average, but I weight with respect to this gradient squared factor. Okay, so this is how it works. Okay, and so this is really an advantage, and we will come back to that. Yeah, so I now will turn to a particular example of reinforcement learning. And then we will see in this particular example that the baseline really helps. But for now, let's set aside the baseline and the more complicated calculation. Let's just ask, what would be the simplest example of reinforcement learning that we could construct? Well, I don't know, but certainly if I want things to be probabilistic, there should be more than one action. Maybe there should be two actions. And the state, well, maybe my state should be a single variable. So I decided just to take a random walk. I have a random walker. The state is really the position. The action is to go up or down. That is, go +1 or -1. And the only thing that is special here is this random walker doesn't always just go 50-50 up or down, but it's the policy that tells me where it goes with which probability. Yeah? So you could call this a biased random walker that maybe is more likely to go +1 than -1. It's the policy that will tell me. This is a very simple case because, for example, the policy doesn't even depend on the state. It doesn't depend on the position. It doesn't need to in this game. Yeah? So the policy will always be the same independent of the position. So that's already different from the more general case. And then also, I don't really have a reward at each time step. I will only introduce a reward at the final time step, and that I take to be how far along I got. So the reward at the final time step is simply the position, which obviously means I want to go as far as possible to the positive side of the coordinate system, because then I get a large reward. And now you can all tell me what's the optimal strategy for this walker. How should the policy look like? Yes, it should straight go to positive values. The probability to go up should be always 1, and the probability to go down should be 0, of course. So what I'm showing here is obviously far from the optimal strategy. It's still probabilistic. It sometimes goes up and sometimes goes down. Then it gets this reward at the final time step, and the return in this case is the same as this final reward, because all the other time steps have no reward. Okay. The good thing about this is the policy is so simple, it's just this probability of going up or down, that I can represent everything analytically. I don't need a neural network or anything. I don't even need to do numerics with a table. I can really literally calculate everything analytically. Okay. So now the first thing, so there are a number of formulas here, but really it's not difficult. The first thing, I have to parameterize my probability, my policy. And depending on this parameterization, at least the formulas will look slightly different, yeah? Because I have now to choose, I will have to choose how the probability depends on the parameter. So there will be a single parameter that I call theta. Usually there's this long vector, but now there's only a single number, theta. And this defines the probability to go up. And I take it to be in this form, and you recognize an old friend. This is the sigmoid, yeah? Or the Fermi distribution. So if theta is very large, then this e to the minus theta is 0, so I get 1. If theta is very small and negative even, then this explodes and I get 0. Okay. This is all. I don't need to independently specify the probability to go down, because probabilities are normalized, so this is just 1 minus what is displayed here. Okay. And the return, the overall return, I already told you, is just the position at the final time, capital T. So I specify there's a time interval, capital T, I don't know, some number of time steps that I fix, and the position at the final time that will define my return. Okay. And so now I can really literally directly calculate my update of this single parameter. Yeah? So here's the formula we know. There's a learning rate eta, there's a sum over all times, there's the return for this trajectory multiplied by the logarithmic derivative. Now these actions AT, they are either up or down. Or if you like numbers, you could call them +1 and -1. Yeah? And so this expression for a particular trajectory Well, it will depend on the particular sequence of what you did. But first, we have to calculate what's this logarithmic derivative. Well, that's not hard because we have an explicit expression of the policy. So d log over d theta, that's a little exercise you should do for yourself. And now you not only want to do it for the action being up, but also for the action being down, because there are these two possibilities. Both of them will occur when I finally calculate here the logarithmic derivative, because a can be both up or down. And so I did this. I will always display both of the options simultaneously. So here you find the formula looks like this. I can re-express it in terms of the probability itself. That's because the derivatives here are super simple. And the plus sign is relevant if the a equals up, and the minus sign applies if the a equals down. This is just a very simple exercise. And then just by looking at this formula, you can simplify it a little bit. You find it's just plus minus 1 minus the probability itself. Okay? And to make it really explicit, if I'm going up, this is just 1 minus the probability to go up. If I'm going down, it would be minus 1 minus the probability to go down. But if I re-express this in terms of the probability to go up, this is what I get. Yeah? It's really just very simple algebra. But now the nice thing is, I have explicit expressions for this logarithmic derivative, depending on whether I went up or down. The return, of course, is just calculated for the full trajectory, like here. And then the sum over all times can immediately be calculated, because whenever I go up, I will have a certain contribution, this one here. Whenever I go down, I have another contribution, this one here. And to sum it all up over all times, I just need to count how many times did I go up, how many times did I go down, and then I multiply with these values. So I multiply this first contribution with the number of times that I went up, and the second contribution with the number of times that I went down in this particular trajectory. I have not yet averaged over trajectories. It's just for this particular trajectory that I'm thinking of right now. So the sum over times, d log over d theta, is, well, I multiplied the first thing with n up and the second thing with n down, and then I used that n up plus n down equals the full number n of time steps, and so this is what I arrive at. Yeah, n up minus n times the probability for up. If you think about it, so first of all, it's super nice that we can explicitly work this out. This is almost never possible. And second, if you think about this particular expression, it also has a nice interpretation, because if you work out what's the expected number of up steps, well, that's the number of total time steps multiplied by the probability to go up. So it's exactly the second part here that I subtract. So what we see here is essentially the actual number of up steps that I took minus the expected average number of up steps. And so this is somehow this sum. And now you can already guess somehow where this is going and why this makes sense. If I, or maybe I have it on the next slide. I think I have it on the next slide. So maybe let's now take this together with the return that I get. Again, because in the end, I like to express everything in terms of the actual number of up steps that I took, because this will be the only real random thing in a given trajectory. This defines everything. All the other steps have been down, obviously, and the total number of steps is well defined. Yeah? So n up will be a random variable that characterizes my trajectory. I don't need any more. And so I also want to express my return, the overall reward, in terms of n up. And I can do this easily, because the position at the end is obviously just the number of up steps minus the number of down steps. The number of +1 moves minus the number of -1 moves. And by using that, the sum of them is n, I can also write it like this, 2 times n up minus n. Okay. And so now coming back to this reinforcement learning update, here it is again in the original version, But now we've calculated both the d log, d theta, and the return. I can plug these formulas in, and then I get this expression here. The second part comes from the d log over d theta, as I explained just now, and the first part comes from the return. Okay. So now we can check whether this makes sense. So, for example, initially I might initialize a random walk that just goes 50-50 up or down. So pi would be 1/2. What is my update? Delta theta here. What is my update? Well, I just insert this expression, but also the expected number of up steps is just n½ for this simple case. So I get n up minus n½ squared, which, if you think about it, is just the variance of the number of up steps, because n½ was the average. Yeah? And I can even calculate this, because the number of up steps, if I have a unbiased random walk with half-half probabilities, will be just, this will be n², if you remember. Because for a binomial distribution, if you have n attempts, and the success probability is p, then the variance is n times p times q. Q is 1 minus p. Yeah? Now in this particular case, p is 1/2, so it's n times 1/2 times 1/2 is n², and then combining with a 2 in front, I just get eta times n². So the precise value maybe is not the most important thing, but it's positive. Does this make sense? Well, yes, it does, because we already guessed that the optimal strategy is when we always go up. I start with a strategy where I only go up 50% of the time. I should improve this probability. How should I change my parameter theta to improve this probability? Well, if you look at how it was parameterized here, if theta gets larger, then the probability gets larger. So obviously I want to increase theta, and this is exactly what this formula announces to me. So in the beginning, this reinforcement learning policy gradient will automatically push me towards bigger probabilities to go up, which is exactly what I need. Okay. And this result, of course, would have come out regardless of how I parameterize. I could have parameterized in any other way with respect to theta. Maybe sometimes the step in theta would have become negative, but the resulting change of my probability would always be positive. I would always have a tendency to push towards going up, because that's where the reward is. Okay. Is this clear so far? This is probably the simplest reinforcement learning example you can construct. And it's very rare that you can get analytical expressions. Yes, please. Okay, because usually as soon as, for example, you have your states entering here, then in order even just to calculate these expectation values over probabilities, now suddenly you would need to know these transition probabilities for your environment to go from one state to the next, and it might be, and that might happen to be a very complicated probabilities. Even if the environment is simple, but if your policy depends on the state, then again it becomes a very complicated problem. Then usually we wouldn't be able to do simple things like, oh, let me just sum over all times and let me express this in terms of the number of steps where I took one action versus the number of steps where I took the other action, because now everything depends on the state you are in. Yeah. So there are many good reasons why it's almost never the case that the things are as simple as this. And so almost always you will need to actually sample numerically these trajectories. Yeah, so I mean, this upstate rule is of course something general, except, okay, here I already dropped the state, but apart from that, this is our general update rule. But an expression like this is very rare to have. Yeah. Okay. Good. And so now, this was just the case at the initial point in time. Yeah? But we can also, since this example is so nice, we can also calculate our update for completely arbitrary probabilities. So then we can understand the full behavior during training. Because again, I have these expressions, I can do a little bit of algebra, and in the end I will see I have terms that are quadratic in the number of up steps and other terms that are just linear, and then I can write it in terms of the variance of the number of up steps and this very simple expression. So this expression, of course, is the average of n up minus the average of n up is just 0. So I just end up with a variance, and as I just told you for the binomial distribution, this is n times probability times 1 minus probability. Yeah? So this is the fully general expression for our update, averaged over all trajectories already. And just to display this function here, I display the right-hand side, I display this function as a function of the probability to move up. 1/2 was where we imagined we started. You see it's positive. It's actually always positive because it's always a good idea to improve this probability because we always want to move up. But you also see that if I'm not near this probability of 1/2, then this expression will become smaller and it will even vanish near the extremes of the probability. So that means, well, for one thing, it means if the probability to move up is already 1, we will not increase it even more, and probably we shouldn't. Okay? But there's another thing that might be considered a problem. If the probability started out 0, then you actually don't move your parameter either. And that's not so nice, because it could mean you get stuck in the wrong solution. Because probability of moving up being 0 just means you're moving down all the time. So this may be a problem, but the rest is very nice. You're always moving in the right direction. And so now, this of course was only the expected average gradient. But in reality, you never average over all trajectories. And usually in more complicated cases, you would not be able to calculate this analytically. So this analytical calculation, of course, gives us an average over all possible trajectories. But usually we cannot do this. So usually we have to resort to numerics by stochastic sampling of trajectories. And that's when fluctuations come in. Yeah, please.
Our function would only approach the 0 asymptotically?
Yes. Yeah, so usually the asymptotic solution, I expect it always to be reached only asymptotically. Something like depicted here. Now here I want to discuss the fluctuations, but you also see the average trend, and of course it gets slower and slower. Yeah, this is similar to even the neural network gradient descent on its own. So as it approaches, maybe in the simplest case it might be an exponential approach or whatever it is, but it's usually not going directly there and then stopping. Yeah. Okay, so here I did the actual numerical simulation. So here I sample trajectories, I sample the number of up steps that I took, and then I apply my update formula, no longer having averaged over all trajectories, but just doing the stochastic thing. And you see here I let it run 3 times. And you see very, very strong fluctuations. You see there's always a trend to go up, and that's good. That's also what we expected on average. But there can be strong fluctuations where you even go down again. This is a little bit similar to our stochastic gradient descent for neural networks in general, because even there, in principle, your cost function should always decrease, but sometimes it increases again because you make the wrong direction step. So you see here you have strong fluctuations. If you were to guess where the fluctuations are largest, if you look very closely, you can already recognize it. Near 0.5, there don't seem to be too bad fluctuations. I always tend to go up. Yeah. Near the final state, I also nicely stay there. So also no bad fluctuations. But in between, there seem to be really big fluctuations. So please keep this in mind. Yeah? And as far as I remember, this was done with a batch size of 1. So there is actually no batch, but I have a relatively small eta learning rate parameter. Yeah? So in the limiting case of a very, very small eta, I would effectively sample or average over many samples over many trajectories, and then these curves would become smoother. Okay. Now, since this is such a great example, we can even calculate these fluctuations that I expect. So the not only the average gradient, but also the fluctuations of the right-hand side of my update equation. And so now you see here the right-hand side of my update equation has this general structure where I just introduced a few helper variables. And the only fluctuating variable here is y, which is the deviation of the number of upsteps minus the, from its average, the deviation of the number of upsteps from its average. And so x is really the update that we take during one step. And so what I'm interested in is not only the expectation value, we already checked this has a certain shape, and it's good, but I want now to calculate the variance of this. And I don't go through it here. It's a nice little homework exercise. You see x is itself quadratic in the number of upsteps. So if you want to calculate the variance of x, you will arrive at expressions that are quartic. They have the number of upsteps to the 4th power. And then you need to think a little bit, but it can be done. And so now here I'm plotting the spread of x, so the square root of the variance of x. And you very clearly see this green curve. It becomes maximal not in the center, where the probability is 1/2, not at the edges, at the extreme limits, but somewhere in between. And this directly reflects what we also see in the numerical experiment. So the fluctuations are largest when the probability is neither 1/2 nor 1, but somewhere in between. Then I get really large fluctuations in this particular example. Yeah. Okay, and so you see here for a batch size of 1, this is the expected update, so the average of x. The green is the spread of x. And then you see that unfortunately, at least the way it's displayed here, what you see is that the average is below the spread. So it's pretty bad. Of course, you can counteract this by, for example, taking a larger batch or taking a small learning rate, because then effectively you are averaging over many trajectories. But the spread is pretty bad. You can even work out, because everything is analytically available, how this spread scales with the number of time steps, and it's a non-trivial power up here. Okay, and now I want to, so to speak, advertise a little bit the optimal baseline, in case you already have forgotten it. This was the way to try to reduce the fluctuations. And this is really, again, it's possible to handle this analytically here. So this is the expression, this is just a translation of the expression we had for the optimal baseline to this particular case. So here you can calculate B, and you can really work it out. And then you can take your alternative update rule, where this right-hand side has been changed a little bit by subtracting this baseline. So this is what results if you subtract the baseline B from the return. And then what you can see, and then you can go ahead and calculate the spread of this alternative update rule. And you see it's here the red line. It's much, much better. It doesn't have these gigantic fluctuations that we have out here. And so this is really much better. Okay. But as I said, this is a very rare case, to be able to calculate all of this. Okay. Well, okay, so this slide is just to remind you that even though the message seemed to be a little bit pessimistic, when you take many small steps, or you just average over a batch, then of course you can always reduce the fluctuations in this sense. Yeah. So even if you didn't take a baseline, but were to average this update over sufficiently many samples, then you can bring down the spread simply by a factor 1 over square root of m in the usual manner, that your estimate gets better by 1 over square root of m if you take m samples. Okay. So, so maybe this is a good time to announce a possible homework. Take this example, for example, and try to actually implement the reinforcement learning update, including the optimal baseline. Because what I showed you here is just using the analytics. I demonstrated that the optimal baseline should make everything so much better. But it would be great to redo this plot, including the optimal baseline, and then all these curves should really be much better and converge much more easily to the right solution. Okay. Okay, maybe in the last 5 minutes I already start with the second simplest example for reinforcement learning, or at least define it. So now I want to come to an example where the state actually matters, where the policy should depend on the state. I still want to keep the relative simplicity of the random walker, so my state is still a position of some random walker. The action still has to do with emotion, but now I want to change it a little bit. I want to say the action is just move ahead or stay, and you get rewarded if you stay for a really long time on what is called a target site. So this is how the state dependence comes in. Yeah, you need to know which site you are on, and you need to understand that once you have reached the target site, you should stay. But since you want to get a really large return in a limited number of time steps, you should really move very fast to the target site, as fast as possible, and then stay there for a long time. So this is the optimal strategy. Yeah? If you get rewarded for being on the target site, but you don't start there, but you start somewhere else, then you need to move as fast as possible, and then you want to stay for a long, long time. Okay, so maybe let me discuss the details of this example next time, unless there are some questions already here. If not, okay, so see you next time.